Welcome to this presentation. My name is Dietrich Vermetten, and I will be presenting on behalf of Konstantin, Pascal, and Carola our paper on instance selection or algorithm selection in the context of numerical optimization. So we're talking about algorithm selection. So we have some kind of function, some kind of algorithm, and if our algorithm performs well with the function, then great, then we're done. But usually we don't have just one function, we might have multiple ones we want to perform well on, and we don't have just one algorithm, we have multiple ones. And our algorithm that works well on one function might not work well on the other, and vice versa. So we get some algorithms that are working well on some and not on others, and thus there's complementarity in our portfolio of algorithms. We have some problems where one algorithm works well and not other, so there's some complementarity in our problems. And algorithm selection aims to exploit this complementarity. It aims to find which are the strengths of these algorithms, the problems that I care about. But we do not really focus on this algorithm selection part itself. We focus on how do we select these problems that we want to use to create our algorithm selector. Because in the end we might want to apply to some unknown set of problems, but we have control over what we feed into it in the training phase. Since we are in the black box optimization context, the common practice, at least in the case of continuous noiseless single objective problems, is to use BBOB, the suite from the GECCO platform. It contains 24 functions that you can each instantiate in different ways, so you get the same kind of landscape, just a slightly different version of it, designed to have specific high-level properties. So you have, on the one hand, you have sphere functions, on the other hand, you have very highly multimodal functions and other things in between. And so if you are to create an algorithm selector in this kind of context, then the main question that arises is, how do you create a fair train testing split to evaluate your selectors? If it's fair going further, how do you do fair cross-validation? But it all starts with splitting somehow your functions into training and testing. And there are two main ways to do this. One is to do it function-based. So then you leave out one or maybe multiple functions and you train on the rest. But that has the problem that it leaves out problems that have been designed specifically to have different high-level properties. So important aspects of these functions might not be represented in the training set at all, and then you're trying to generalize to something that explicitly is not in your same kind of distribution. So that doesn't really work perfectly. On the other hand, because we have this instance generation procedure, we might do it instance-based, and we leave out some instances of problems. So that means we might have one instance of a Rastregan function, but not another one. And that works, but the question there is, are we not being too close with our training and testing sets? Because we have instances that are only slight transformations, or intended to be only slight transformations of these functions. So maybe it's a bit too optimistic to just leave some instances out. And this is where we get to the test suite that we're actually going to be using. So it's the Many-Affine BBOB generator, which is a generator that uses weighted affine combinations of BBOB functions that have been rescaled and the location of the optimum moved around and can combine multiple of these functions together. So instead of relying on this set of 24 from which we have to choose a selection, we have this generator that can create, based on the 24 functions as components, arbitrarily many instances from which we can do selection. So this generator gives us a huge space for doing this kind of setup. And the question we are aiming to answer is to find a way to select the most informative training set, or the training set that allows us to get the best performance on unseen data. And the most obvious way in which we can select instances is just do it uniformly at random. We have some kind of generation process for these instances, just sample that a bunch of times to get our instances. And that gives us an unbiased representation of the functions that we can generate. But there's an alternative that we are interested in testing out, and that's to maximize the diversity of the training instances. And with diversity, we mean diversity in terms of low-level landscapes. So what we do is we generate instances, we characterize them using landscape analysis. We subselect some of these features, and then we build up our training set by greedily creating sets of instances by picking the one that is most different from the ones that we already have in our set. So we greedily build up an instance set based on diversity in landscape space measured by ELA. And then as a final comparison, because we have this Many-Affine BBOB generator, the BBOB functions are components in these. So all functions we generate are some kind of weighted combination of BBOB. So we can just use these component functions themselves. So the weights of 1 and all zeros for anything else gives us rescaled BBOB functions. And we can train on those to kind of simulate what would happen if we train on the 24 functions we have and try to generalize to this affine setting. So our experimental setup in terms of the instances from which we can do this selection is quite large. We have 11,920 instances in both dimensionalities 2 and 5, and it's constructed by creating 2,000 random weighted combinations of 2, 3, 4, 5, and 6 component functions, and 200 each for 7 to 24 components. Plus added to this the first 5 instances of each of the BBOB functions, with the same rescaling as is used to create the components. And we visualize this space using a PCA to give you an idea of what this looks like. We have this for 2D and for 5D, but we will be focusing on the 2D case, which you can see here. And if you look at the colorful dots, so these are the original BBOB functions, while all of the blue to yellow smaller dots in the background are the affine combinations, where the color indicates how many different components are combined. So the very dark blue ones are 2 components, and then the yellow ones are up to 24 components. And we see here that the affine combinations do fill in the instance space in this projection quite nicely. But as we get more components, things start getting closer and closer together, and we start to really arrive at one small part of the space. While we really, with the few components, we cover more of the area between the other functions. So then let's take a look at how this interacts with the instance selection setup that I described before. Well, we repeat the greedy process that I described up to 10 times for different training and testing set sizes, and we try to avoid overlap with sets of the same size. So if we create test set of size 120, then the first 120 that we have selected are removed when we go create the second set of 120. And to give you an idea of what this looks like in this previous PCA space, we have 5 random and 5 sets greedy selected. And you see that the random do more go towards this space that was highly concentrated, while the greedy do spread out more over the whole instance space. Then we need some algorithms to be able to see how algorithm selection works out. So we have a portfolio of 8 algorithms, the modular CMAES and differential evolution, plus 6 algorithms from the Neverget library. We use IOH Profiler for benchmarking. So we have 15 independent runs on each instance. We look at anytime performance, so area over the convergence curve, or area under the ECDF if you want, with a budget of 2000 times problem dimensionality. So we have about 12,000 instances, so you can imagine that this dataset becomes quite large. And the first thing to do is to see how well algorithm selection can perform in the first place. So before we even do any selection, we want to see what is the potential that we can achieve. So that we can measure as the difference between the single best algorithm, so the best out of this set of 8 algorithms, against choosing the best on each individual instance. So that's the virtual best solver or an oracle, whatever you want to call this. And we can look at that in figures like this, where you see on the x-axis the single best algorithm, so the modular CMAES in this case, and on the y-axis the performance of each individual algorithm. And things that are above the diagonal are cases where the algorithm that is listed performs better than the single best algorithm. And we can aggregate that into a single measure as the VBS-SBS gap, and then we get some kind of amount of performance we can gain by moving from selecting only one choice everywhere to selecting the perfect algorithm for each individual case. And if we do that for all subsets of algorithms, then we see that while with all 8 algorithms present, we have around 0.05 area we can gain by making the perfect algorithm selector. We also have subsets like the one without modular CMAES, where we can gain around 0.11 of this same measure. So we can have a lot more performance complementarity if we do not include the modular CMAES in our portfolio. So that's how we end up with a portfolio of 7 algorithms. With this portfolio, we can then look at how well the algorithm selector performs by measuring the gap between VBS and SBS that is closed by the algorithm selector. So how much closer does it get to this perfect oracle that always makes the right choice relative to the baseline of making one choice overall. So we train and evaluate this on sets of 120 instances, where we make 10 disjoint folds, trained either on the random technique, the greedy technique, which is this maximizing diversity in landscape space measured by ELA, and as a baseline the 120 BBOB instances we have. And then we evaluate on the same set. So that's why the diagonal here is a full 100%, because we train our model to have a perfect accuracy on the set that it's trained on. And then we see the evaluation. We see here random evaluate on random, which looks quite well. We see compared to the greedy evaluate on random that this one that's trained with random samples is better. And for the greedy we see the same thing. So greedy evaluate on greedy is better than random evaluate on greedy. And BBOB just doesn't really generalize to either of the two types of texts. And this same approach is the one we take for different sizes of training sets. So we can aggregate this whole set of data into one single measure of the scare on all of the faults that we leave out. And that gives us this final aggregated performance. So we have different training set sizes, different testing set sizes, and the same kind of conclusions still hold. I will not go into a lot of detail on the exact numbers here, but the main thing to take away from this is that we do see that training on random and evaluating on random is better than training on greedy evaluating random, and the other way around for evaluating greedy. But as we increase our training set size, we do gain quite a bit of benefit and enough to overcome this difference in distribution. So to wrap this all up, we find that instance distribution does matter for algorithm selection. That's not something we have just found, that's something that is well known. And we've just confirmed here that matching distributions is of course preferable. If our training set matches the distribution of our testing set, things work fine. You can of course increase your training set size to mitigate differences in distribution, but the question of how you can actually select ideal sets that generalize to different kinds of distributions, so both to diverse sets of instances and to random sets of instances, is still a little bit unclear. But at least we've shown that within this playground provided by these affine combinations, we can do experiments and figure out on a data-driven way what algorithm selection looks like without being limited to the small set of instances that people usually make advantage of.